This is a quick note for binary representation, actually representation versus number of possibilities. We particularly important to note here. So, you know, as a special case, we want to look at the binary representations, right? Binary representation on bits. And we also want to look at what's the range of representation, and what is like the maximum and the minimum. That's the same as the range, maximum and minimum numbers on a given number of bits. So this is a quick video to show you guys that. And before we start, I want to bring up something that we're going to study later, but it's a very simple mechanism, which is the number of possibilities with unrestricted combined choices. We're going to call this product rule. And we're going to get to this at Cartesian products. Later. So my point here is, here's a example intuition. What if I have 3 shirts? Let's call them shirt A, shirt B, and shirt C. And I have maybe 2 pants, pant 1 and pants 2. And maybe I have 4 hats. Let's call them hat A, hat B, hat C, and hat D. The question is, how many ways to dress up? Again, unconstrained. That's a very important aspect of this principle here. Any shirt choice goes with any pants and any hat. So the way I want you to think about this is, you know, I could have, here's the shirt I'm going to wear, and here's the pants I'm going to wear, and here's the hat I'm going to wear. There are 3 choices, possibilities, right? Because the 3 shirts, and this is 2 possibilities. And this is 4 possibilities. And that results in 3 times 2 times 4 possibilities combined. Again, this is what we call product rule. Remember, it's absolutely essential to have no constraints. For example, if shirt A doesn't go with hat A, they're the same color, this won't stand, right? So of course we can make this product 3 times 2 times 4, that is 24. And that's how I get it. We're going to come back to this rule when we study sets and basic counting, but I think most of you understand that I can have 3 ways to put the shirt, 1, 2, 3, 2 ways to put the pants, and now any shirt goes to any pants. There's 6 total possibilities, right? And you can enumerate some of these possibilities. I won't enumerate all of them, but I'll enumerate some. I can do shirt A with pant 1 with hat A, right? That will be one possibility. I can do shirt A with pant 1 with hat B, so on and so forth. Or I can do shirt A with pants 2 with hat A, shirt A with pants 2 with hat B. So again, we're going to talk about Cartesian set products follows these rules. But I want you to understand that mechanism because of what I want to show you. This is the note that we have there on the website that talks about this kind of thing. So let me add a page here after this page, right? So we can continue with this discussion. This is just an intuition. I'm not trying to prove anything here. Now let's move to binary, right? Let's say binary. We added a page, but we lost the right. So now let's move to binary. Say I have 6 bits. That's given. Here are the bits 1, 2, 3, 4, 5, 6. Each bit could be, of course, in binary 0 or 1. So that is 2 possibilities for the first bit, and then 2 possibilities for every bit. So how many total possibilities combined on all 6 bits? Well, again, very important, this is unrestricted. Any choice on first bit goes or is valid with any choice on second bit, and so on and so forth. So again, I have my bits here, and if I have 2 possibilities here, 2 possibilities 0, 1, 0, 1, 0, 1, 0, 1, right? We can actually write those possibilities out here. So this is 0 or 1, 0 or 1, 0, 1, 0 or 1, 0, 1, 0, 1. So the answer is how many possibilities? Answer is 2 times 2 times 2 times 2 times 2 times 2, because any one of these individual choices has either 0 or 1. So that's 2 to the 6 possibilities. So conclusion is I can represent 2 to the 6 things on 6 bits. Now, the things, of course, for us, we want them to be numbers. But we can represent other things: food plates, people, courses, universities, political candidates, whatever you like. But the point is, you can only represent 2 to the 6, which is 64 total possibilities. So now, if we do this unsigned, we remember we have 64 choices, or let's not call them choices. Let's show them just 64 numbers that we can represent. We're gonna choose a range. This is a very important concept here. The range is from 0, including 0, to 63. That, of course, is 0, 1, 2, 3, all the way to 63, right? This set. We call them, I put this column here like in MATLAB, that's the range 0 to 63. All the integers, including 0, including 63. So all unsigned means all positive. That's unsigned. So I'm not worried about the sign. It starts with 0, goes up to 63. I can represent those, and that's the typical binary representation. Or if I want signed, that means negatives plus positives, but still 64 total. So then I get a different range, right? I'm going to put a line here to be clear. Now my range has to be, it's still 64 total options, but I want some positives and some negatives. So the range by default that I'm going to use here is from -32 all the way to 31. That's a MATLAB notation, but I can write it in a set notation. That's -32, -31, -30, all the way down to -1, 0, 1, 2, all the way to 31. Right? That's the same way. It's all the integers starting at -32, ending at 31. Of course, that's I'm going to add another page here. That's still only saying you can represent those 64 things. If you want them to be unsigned, like in here, where you can get the range 0 to 63. That's what we're getting when we represent the numbers. And we have a mechanism for doing so. Or we can get a signed range, and then you get the signed range will be this range. So we need a mechanism to do so. So in here, the actual mechanism, the actual representation is the default one binary that you study. And in here, the representation, sometimes I call that a mechanism, or you can call it a procedure. How do you actually represent this 64 things on binary? That procedure is called 2's complement. There's other ones. 2's complement is not the only procedure you can use, but you can use that. This is described, of course, in the basic regular videos, binary and 2's complement. My point is to give you a sense of how this works in terms of representation, how many things you can represent given that you have those bits. So now to expand this idea to base 10, say I have the same 6 digits. Here they are 1, 2, 3, 4, 5, 6. Now in base 10, the digits are 0, 1, 2, up to 9. So this is 9 possibilities. This is 9 possibilities. 9 possibilities, right? This is every one of those. This is 0 to 9, 0 to 9. Sorry, that's 10 possibilities. I'm thinking of something else. Let me erase a few things. Mistake. Each one of them is 10 possibilities. So all these ranges are 0 to 9. So now, what is the total number of combined possibilities on 6 digits? Remember product rule? Because again, very important, this is unrestricted. Any digit goes with any other digit. So therefore I have 10 times 10 times 10 times 10 times 10 times 10 possibilities. That is 10 to the 6. So now, but actual unsigned range, that's a million, right? Unsigned range, I don't worry about the sign. It's going to be from 0 up to 999,999. That's the range I can represent on. Sometimes I put those brackets on ranges here. That's the numbers you can represent on 6 digits, right? Common sense tells you that if you want more than 999,999, you need more than 6 digits. You need the 7th digit to represent a million. So it's a useful way to think about the representation this way. I have those bits or those spots that I can populate with 0 or 1 bits, or in decimal with 0, 9. How many possibilities are there? That will dictate the range. And that will also dictate the negative range, the 2's complement. How many things, if you start at -32, you can go up to 31 because that would be 64 values on 6 bits. So the rest of the note here that I'm going to go very quickly over it talks about the question, if I have, you know, say six digits, base 10, what is the maximum? This is unsigned. We're not worried about the sign. And you're going to say, obvious answer, the maximum is, like, if you look from a visual perspective, you have 6 spots, and the maximum each spot is 9. So the max gotta be 999,999, because I have 6 things, and the maximum I can put there is 999,999. But if you think about this from an algebraic standpoint, so that's visual, but how about the algebra? 999,999 is actually 9 times 10 to the 5th plus 9 times 10 to the 4th plus 9 times 10 to the 3rd plus 9 times 10 to the 2nd plus 9 times 10 to the 1 plus 9 times 10 to the 0, which is really 10 minus 1 times 10 to the 5th plus 10 to the 4 plus 10 to the 3 plus 10 to the 2 plus 10 to the 1 plus 10 to the 0, which is a geometric series. We'll study that later. And this geometric series, you can see right here, there's a way to prove this formula. That in our case, we use x equal 10, and the n for us, the exponent, the highest exponent was 6. So our formula here is just this maximum value. This is max here, which we wrote this formula for base x equal 10. That's the base, and this is the highest digit. So that's how you get the maximum value you can represent in algebra with this formula. You can see this x minus 1 here, it's exactly 10 minus 1. And this geometric progression here, it's exactly this in a particular case of x equal 10 and n equal 6. So there's a way to do this maximum, to do this formula before, you know, later in the term we're going to get to geometric series. But until then, we can just I'm gonna do this proof right now. So let's prove this formula. Let me get my pen here. So proof. Here's what we're gonna do. We're gonna open the parentheses. So what we're gonna do is to say x at 0 plus x, I guess we call this x at 1 plus x at 2 plus x at n minus 1 times x minus 1. That's what we have, right? We open the parentheses. So now if we multiply x at 0 with this parenthesis, I get x at 1 minus x at 0, right? And then when we multiply x at 1, we get x at 2 minus x at 1. And then when we go multiply the x at this x2 here with a parenthesis, now I'm going to get x3 minus x2. And when I multiply the last one, so I'm going to do dot, dot, dot here. When I multiply the last one, that's x n minus 1, I'm going to get x at n minus x at n minus 1. This is a telescoping series. Nice name. What telescoping means, maybe I should write this in red. Let me see if I can do this really quick. Make this color being red. Okay, telescoping. So how that works, telescoping? That works by saying, look, x1 here is the same as x1, so this kind of goes away. And then x2 goes away with x2, and then this x3 will go away with this x3, and this x minus 1 goes away with minus 1. So if you look at what's remaining, when you add everything up, you get only x at n minus x at 0, because the only guys that did not telescope are those two. They don't cancel each other. So of course, this is x at n minus 1, which is the answer we are looking for. That's a proof that you guys can do right now without knowing about geometric series, which we're going to study later on. And then the rest of the note goes through how does this work with base 10. So of course, being a general base x here, this would work with any base 2, base 16, base 10, doesn't matter. That's the maximum number in there. And then I give you some other exercises for only, this is not mandatory. This is just for people who wanna go a little bit further in this. You don't have to follow this. All right. So I'm gonna talk to you guys about this in the office hours.